Hi, this video will finish up the notes for chapter 4. And this is a lot of math. A lot of math used to do chemistry problems. So let's talk about stoichiometric math or stoichiometry math. There's two issues that we have to deal with. One is atoms don't have equal mass. So if I'm talking about a sodium atom and a chlorine atom, they don't have the same molar mass, 23 versus about 35 and a half. So that's a problem. And you don't use equal quantities. So if I'm talking about, let's say, propane, I'm going to need 3 carbons and I'm going to need 8 hydrogens. So not only do the carbons and hydrogens have different masses, I use different amounts of those. So in the same way that I'm making if I'm trying to make breakfast, I'm not going to use like 1 cup of eggs and 1 cup of salt and 1 cup of pepper. That does not make a good breakfast. I have to use a specific amount of each of those ingredients. So the real usefulness of the mole number is you can calculate the grams of a substance needed for a chemical reaction. So what do I mean by that? I mean that if I've got some substance and another substance, and I want those two things to react, how do I know how much to put in the container to allow them to react together? And the answer is we use stoichiometry and stoichiometric math. So let's do an easy one here. Here's the balanced chemical equation for the chemical reaction of table salt, or to make table salt of sodium and chlorine gas. We don't really need to do this because there's already so much table salt on Earth, but you can absolutely do this. Take elemental sodium, which is very reactive because it wants to give away 1 electron, and chlorine gas, which is very reactive because it's also just trying to do one thing, and in this case, gain 1 electron. If you put these in a container together, you will get a spectacular light show, some heat, and table salt. All right, so here's the problem. What happens if I put too much sodium in? Well, what'll end up happening is I'll have leftover sodium when I'm done. So when I go to use the table salt on my fries and the sodium touches the moisture in my mouth, my face explodes. That seems bad. So what happens if I make sure I don't have too much sodium and I have too much chlorine? Well, when I open up the container to get my table salt, I breathe in the chlorine gas and then I drowned on my own blood in my lungs. Also bad. All I want is to make some fries. Make some flavoring for some fries. So I need to make sure that the number of sodiums and the number of chlorines that I put in the container together, make sure that they run out at exactly the same time. All right, so that's our situation. Let's say that we want to do this reaction and we're going to start off with 10 grams of sodium metal. So my question is, how much chlorine, how much Cl2 do I put in the container to make sure that they both are used at the same, run out at the same time? And the answer is not 10 grams of chlorine gas. And the reason is what we alluded to at the beginning, which is the sodiums and the chlorines don't have the same mass, and I don't use the same amounts of them. And in this case, also I got another problem that chlorine comes as a diatomic, comes as Cl2. So I need to account for all of that. So there's an easy way to do this. And all of your calculations are going to look like this. So it's going to be something like this, where I just fill this template in. Let me pull up another worksheet. Worksheets, stoichiometric. There we go. So your template is going to look like this every single time you do these calculations. It's going to just have this section down here. And then you're going to fill this thing in, stuff in the front and stuff in the back. So let's move this out of the way and talk about why this is what it's going to look like. All right, so I'm going to start upper left-hand corner with the amount of stuff that I'm starting with. And in this case, I'm starting with 10 grams of sodium metal. Okay. I don't care about the number of grams of sodium metal because in this chemical reaction here, It says nothing about grams. All it says is I need 2 NAs to go with 1 Cl2. That's all it says. So I need 2 of those to go with 1 of those. So really what I need to do is I need to know how many atoms of sodium there are in 10 grams. And that's what we're doing here. So I'm going to start off with the mass that I'm starting with. And the reason we're starting with mass is because I can't count this number of atoms. This is going to be billions upon billions upon billions. So what I'm going to do is I'm going to take the molar mass off the periodic table, the 229898 grams per 1 mole. So this fraction is equal to 1 because 1 mole of sodium has this mass. And what I've done with this first fraction is I have actually counted the number of sodium atoms in terms of moles. And that tells me how many I have. In the same way that I could say I have 18 dozen donuts, I don't know the exact number of donuts because I know them in dozens. And so in this case, I'm going to know how many sodiums I have in terms of moles, which is a number that makes a lot more sense since there are so many atoms I'm dealing with in this particular reaction. Okay, so that's my first step. It'll always be my first step. I start with what I'm given, and then I go right into the molar mass. So how do I know that? Well, this says 10 grams of sodium. So I'm going to have 10 grams of sodium down here. So these things cancel out because what I'm looking for in the end is how many grams of chlorine gas I am going to be adding to this 10 grams of sodium. Okay. So again, what I've done here is I've canceled out the grams and I have counted the number of sodium atoms. All right, so now I know how many sodium atoms I have. And so what I need to realize is for every 2 sodium atoms, I need 1 Cl2. So that's what I've done here. For every 2 moles of sodium, I need 1 mole of Cl2. These guys here, right after the grams, they're going to come from the balanced chemical equation. If it's not in the balanced chemical equation, it's not going to be in my template. It's not going to be down here with the math. So that's why this says Cl2 and not Cl. It doesn't say Cl up here anywhere. It says Cl2. The other thing is Cl doesn't exist. Only Cl2 does. By itself, that is. Alrighty. So erase all that. So now what I've done with my second calculation, my second railroad track here, is I've canceled out the number of moles of sodium I've got and turned it into the number of chlorines, this number of Cl2s I need. Great, so now I know exactly the number of Cl2s I need. Since I can't count that, I have to count it a different way, and so I'm going to count it in terms of molar mass. So now I'm going to switch my count of Cl2 into a mass of Cl2. So here's my molar mass. Why does it say 70.906? Because it's Cl2. So I go to the periodic table and I see that chlorine's molar mass is 35.453, and I double that. And so I get 70.906. All right, so let's see what we've done here. We have we've converted my grams, my mass of sodium, into a number of sodium atoms. Then I've switched over from a number of sodium atoms to a number of chlorine atoms. And then I've taken my number of chlorine atoms and turned it into a gram of chlorine atoms. And that's what I'm looking for, grams of chlorine. So now what this is saying is if I put 10 grams of sodium in a container with 15.42 grams of chlorine, they will run out at the exact same time. There will be nothing left in my container except for table salt, which is good because I don't, want my face to explode and I don't want to drown to my own blood. And as a side note, you can tell how much of the sodium chloride is going to be made. Table salt's going to be made. I'm going to end up making 25.42 grams of sodium chloride. I'm just adding those numbers together. Why? Because I know all of this is going to get turned into that. And all of this is going to get turned into that. And there's going to be nothing left in the container. So that's how we do these calculations. That's how I want to see it on your homework. And that's how I'm hoping that you do it when you take quizzes. Because this is the best way to calculate out these molar masses, these masses of different substances. So you can see the first thing I talked about is the 2 problems. The sodiums don't have the same mass as the chlorines, so that's a problem. Also, I need 2 NAs to go with my 1 Cl2. So I need to make sure that I'm accounting for both of those situations. Okay, so we're always going to be starting with the mass of what was given. I'm going to turn my mass of given into a moles of given. I'm going to take my number of moles of given and turn it into the number of moles of something I want. And the number of moles of something I want, turning it into the mass of something I want. And here's the grams of whatever it is I'm looking for. So this template is what we're going to use. And I like the way it looks here. Sorry. So you just fill this guy in. Let's do this one down here. I'm going to cut this out so I can better. I'm going to go ahead and copy that, and I'll go back over to Notes. Let's do a new one. Go right here, Control V. All righty, so let's go ahead and do this problem. So this was problem number 3 off that worksheet you would find on Moodle. I'm starting with 175 grams of nitrogen. So I got 175 grams of this, and I want to know how much hydrogen gas do I need so that they both run out at the same time. The first thing I need to do with any chemical equation is I need to balance it. So to balance this guy up here, 2 nitrogens, now I have 2 nitrogens. This gives me 6 hydrogens, and a 3 here gives me 6 hydrogens. So I'm balanced. Okay, so like the template says, I start off with the number of grams that I was given. So I'm going to go ahead and start off with 175 grams of N2. So I need to convert that grams of N2 into moles of N2. So this will be N2 turning into N2. This is always going to be 1 because that's what the periodic table runs off of, 1 mole of something or other. And then our mass for nitrogen is 14.0067. So I'll double that times 2. And so then this is going to be 28.0134. Great. So I can go ahead and cancel out my grams. And what I've done is I've counted. This first railroad track counts the number of my starting material. So now I know exactly how many N2s I have. Well, I don't want to know about N2s. I want to know about H2s. So I'm going to go ahead and write N2 down here and H2 here. And I need numbers to put here. And the numbers come from the balanced chemical equation. So for the hydrogen, I'm going to write a 3. And for the nitrogen, I'm going to write a 1. That's it. So now what I can do is I can cancel out my moles. So now what I've done is I've turned my number of nitrogen molecules I'm starting with and turning it into the number of hydrogen molecules I'm going to need to react with. Now, I can't use that number because, again, it's too big. So I'm going to go ahead and convert my number of hydrogens, H2s, into a mass of H2s. So it's always going to be 1 here because what I'm doing is I'm going to go to the periodic table and I'm going to look at hydrogen, and hydrogen's mass is 1.00795. I'm going to multiply that by 2, and I'm going to get 2.0159. Okay, so now what I can do is I can cancel out my moles of hydrogen, and what I'm left with is grams of hydrogen. Awesome, because that's what I'm looking for. So grams of H2. So then 175 divided by 28.0134 times 3 and times 2.0159. Should be a smaller, pretty small number. And I've got 37.8 because we got 3 sig figs here. That's it. So now if I take 175 grams of ammonia and I add 37.8 grams of hydrogen gas, the nitrogen and hydrogen will run out at exactly the same time. And so 175 plus 37.8, that's going to give me 212.8 grams of ammonia created. That's it. That's how you do these problems. I'll give you lots of opportunity on the homework to do these, so don't you worry. And I'm always open, as many of you know, to having a Zoom meeting. Not all of you are taking advantage of that, but some of you are, and it's great. Glad to help. Okay, so Now, we're going to do another type of these problems, and this type of problem is called the limiting reagent problem. Okay, so I've got an example here, like a normal example. If I'm trying to make apple pie, and I want to make as many apple pies as I possibly can, when do I stop making apple pies? Well, if I run out of apples, I'm going to stop making apple pies. If I run out of salt, I can't make them. If I'm running out of flour, I can't make them. If I'm running out of, what else do you put in apple pies? Probably a little bit of sugar. Maybe some butter. I actually can't remember. I think it's just a little sugar. Maybe baking soda for the crust. But the mix is just going to be apples, maybe cinnamon. Okay. If I run out of any one of those things, I can't make apple pies anymore. It does not work. So if I have a bunch of stuff and I need to make it react together, one of them is going to run out first. That's just the way it's going to be. So here's my example. Here's the chemical reaction. I'm going with silver metal is going to react with bromine liquid, and I'm going to make silver bromide. Okay, so I'm going to start with 87.5 grams of silver and 75 grams of bromine liquid. How much silver bromide can I make? Well, the issue is one of those two substances is going to run out before the other substance, and that's what makes this a limiting reagent problem. That I'm going to have to figure out who runs out first. So how do I do this? I run two calculations. I'll run a calculation for every single one of the reactants I have. And in this case, I've got 2 reactants, so I'm going to run 2 calculations. If I had 5 reactants, I'd have to run 5 calculations. All right, so I start off with the amount of silver I was given. So here's my amount of silver, so I go ahead and put it in there. I convert my grams of silver into moles of silver. So now I have counted the number of silver atoms I have in 87.5 grams. But I want to know how much silver bromide I'm going to make. So I'm going to turn my moles of silver into moles of silver bromide. So what this is doing is counting, if I had this number of silvers, how many silver bromides could I make? And how do I get these numbers here? I have a balanced chemical equation, so I throw 2 and 2 in there. And so I have a number of silver bromides I'm going to make. I don't care what the number is. I want to know what the mass is. So then my moles of silver bromide cancels out with moles of silver bromide. And 187.722 is the mass of 1 silver plus 1 bromine off the periodic table. And again, you see that it's 1 mole in both of these because these numbers came off the periodic table. And so they're always versus 1 mole of that substance. And so I calculate 152.316 grams of silver bromide. Great. Can I make that much? I don't know. The reason I don't know is the bromine going to run out first? Let's find out. So I'm going to go ahead and take my 75 grams of bromine and put it in here. I'm going to convert my grams of bromine into moles of bromine. So my grams cancel out. So now I have counted the number of bromine molecules I have in 75 grams of bromine molecules. Again, I don't care about that number. What I care about is I want to know how much silver bromide I'm going to make. Okay, so I'm going to take my bromine and my silver bromide, and I'm set them opposite each other. My bromine, moles of bromine cancel out. And so now with this second calculation, second fraction here, I've converted the number of bromines I've got into the number of silver bromides I'm going to make with that number of bromines. And this 2 comes from here, and this 1 comes from there. And so, I can't count these silver bromides. I need a mass of silver bromide. So what I'm going to do is, this number here, again, is that same number off the periodic table. So my moles of silver bromide cancel out, and I've got grams of silver bromide, and that's all that's left. And you can see that I can make 176.248 grams of silver bromide. So my question is, can I make 176 grams of this? And the answer is, I cannot. Nope. I can only make 152.316. The moment I've made 152.316, I have no more silver. All of the silver is gone, so I can't make silver bromide if I don't have any silver. So why do I have this bigger number? Well, this bigger number is assuming that I have enough silver, and in this case, I don't. So you will always take the smaller number. If you had enough apples to make 10 apple pies, and you had 7 crusts, you can only make 7 apple pies. Even though you've got lots of leftover apples, I can't make apple pie anymore because I have run out of crust. And so that's the situation here. I can't make 176 grams of silver bromide because once I've hit 152, I don't have any more silver and the reaction is over. That's a limiting reagent problem. So you do 2 separate railroad track calculations to determine how much you could make with each of those, given that you have enough of the other, even though you're not going to. And then whichever number is smaller, that's the amount you could make. So the other question you could be asked here is, what's left in the container? So we have already determined from this calculation that I am going to make 152.316 grams of silver bromide. Awesome. So I know I have this much stuff in the container. I also already know another piece of information. And that piece of information is I'm going to have 0 grams of silver left in the container because that's the one that runs out first. So now the question is, great, how much of the leftover bromine is in the container? Since there's only 2 reactants and 1 product, this turns out to be super easy. How much stuff did I put in the container? Oh, all right, I put 87 grams of silver and I put 75 grams of bromine. So I got 162 grams of reactants. How much product did I make? I made 152.316 grams. All right, so I've got 184 grams of leftover bromine in the container. How do I know that? Well, since I put in 162.5 grams of stuff, there still has to be 162 grams of stuff in the container. And I know 152 of it is the silver bromide, and none of it is the silver. So anything that's left over is my remaining bromine liquid, my BR2. That's it. I'm going to give you another example here, so you can walk through this one. And if anybody has any questions, of course, you can get a hold of me. All right, so the last thing we're going to talk about is reaction yield. So this calculation is the calculation you needed to do lab 3 that I should make lab 6 when I teach this online class again, and I will. I'll make that lab 6. Let's say that. Looks like there's a missing letter here. T. Missing key T here. Okay, great. Okay, so let's talk about how reaction yield would work in the real world. So many a Sunday I have made pancakes, and the recipe for pancakes, the pancakes when we're using Bisquick is 2 cups of Bisquick, 2 eggs, and 1 cup of milk. All right, and it says I should be able to make 14 pancakes. I can never make 14 pancakes. My pancakes are too big. I don't get all the stuff out of the container, the mixing bowl. So I end up making, like, say, 12 pancakes. All right, so I only made 12 pancakes. Okay, so 100% yield would be 14 pancakes, but I only made 12 pancakes. So the calculation to determine how much I made, what my percent yield is I actually made 12 pancakes. I was supposed to be able to make 14 pancakes. I multiply by 100 and I get some percentage of yield. So I don't know, what is that? It's only 75? Oh, no, sorry, that's not right. Looks like 86%. My yield was 86%. Okay, so instead of having 100% yield of 14 pancakes, I'm only got a yield of 12 pancakes, which leaves me with an 86% yield. How does this work in the real world? Well, let's say that you were making aspirin. You take a salicylic acid and acetic anhydride. You mix those guys together and then you make aspirin. If you were in a face-to-face class, we would be making aspirin. And that aspirin ends up, there's almost no way for you to make all of the aspirin that you're supposed to make. You'll do a calculation. You can say, oh, I should be able to make this number of grams of aspirin, given the amount of starting materials. So in the same way, up here, that we said we were going to make 152 or 176, what we're going to say is these are the theoretical yields, but what if I only made 150 grams? Well, then I'd take 150 divided by 152.316 and then determine my percent yield. So down here, what I'm going to end up doing is taking how much I should have made divided by, what I did make divided by what I should have made multiplied by 100. So in this example, if I was making aspirin, and let's say that my calculation said I was supposed to make 6.11 grams, and when I was done, I only had 5.2 grams, then my percent yield in this case would only be 85.1%. Okay, how does this happen? For the most part, it happens for two reasons. The main reason, a main reason is you're switching containers when you're putting this stuff together, and when you do that, you lose some of the stuff behind. You can't scrape it all out of the container, so you're always going to lose a little bit to container transfer, which is why if you can take a chemical process and make it in one pot, everybody's happy because you don't have these losses due to chemical, due to switching containers and leaving behind residue. And the other part, especially with organic chemistry, if I'm going to try to make something like aspirin, organic chemistry is complicated, and what you'll end up doing is making a lot of aspirin, but you'll also make other substances. And those other substances aren't what you want, so they reduce your percent yield. So the people who are making, say, a leukemia drug, when they go to make that leukemia drug, every time they switch containers, they lose a little bit of what they could have made. And when each time those chemical reactions occur, they're going to make something other than that they want. So they're going to have to filter that stuff out, and now they lost mass. So if they're in the 90s, they'd be super happy with that. But there are lots of chemical processes where you start off with, say, 100 pounds of stuff, and you end up with, 3 ounces of the thing that you actually wanted. And obviously, that's a problem. So if you can increase that yield, then that's what you're looking for. So in your lab, you will have to calculate how much of that precipitate you were supposed to be able to create, yet how much you did create. And then you will use this theoretical yield calculation, percent yield calculation. And that's it. That's all I have for all of chapter 5, or chapter 4. And I'm gonna guess we have lots of questions with this one, with the homework, but you're gonna see this for a week now in homework questions. And feel free to stop and ask me for help.